Hey B, I've been revisiting combinational logic design lately, specifically thinking about implementing some complex functions. Where do you usually start with a problem like that?
Hi A. For complex combinational logic, I usually start by clearly defining the truth table for the desired function. It lays out all the input combinations and their corresponding outputs, which is crucial.
That makes sense. Once you have the truth table, what's your preferred method for simplifying the Boolean expression? Karnaugh maps or Quine-McCluskey?
For up to 4 or maybe 5 variables, I find Karnaugh maps visually intuitive and quite efficient. Beyond that, the Quine-McCluskey method becomes more systematic and less prone to errors, especially for a larger number of inputs.
Ah, yes. The visual aspect of K-maps is definitely helpful. Have you encountered situations where one method clearly outperforms the other?
Definitely. For functions with many don't care conditions, K-maps can sometimes lead to a simpler minimal expression more quickly due to the flexibility in grouping. However, Quine-McCluskey handles a large number of variables and prime implicants more rigorously.
That's a good point about don't cares. How do you typically handle them in the Quine-McCluskey method?
We treat them as minterms during the prime implicant generation phase, allowing them to be included in groupings to form larger implicants. However, when selecting the essential prime implicants, we only consider those that cover the must-be-one minterms.
Interesting. It sounds like a balance between inclusion and necessity. Now let's say we've derived a minimal Boolean expression. What are some of the practical considerations when implementing it using logic gates?
That's where things get interesting in the real world. We need to consider the availability of specific gate types. NAND-only or NOR-only implementations can be advantageous sometimes. The number of inputs per gate, fan-in, and the propagation delays, which can impact the overall circuit speed.
Fan-in is crucial, especially for complex expressions. What's your strategy when you encounter a term with more literals than the available gate inputs?
We typically break down the large AND or OR gates into a cascade of smaller gates. This introduces additional delay, so it's a trade-off we need to analyze based on the application's timing requirements.
Right, the speed versus complexity trade-off. Have you seen a shift in how these implementations are done with the prevalence of programmable logic devices like FPGAs?
Absolutely. With FPGAs, the focus shifts from minimizing the number of discrete gates to efficiently utilizing the available logic blocks, like LUT's lookup tables. The synthesis tools handle the gate-level implementation based on the HDL code.
So in an FPGA context, the initial Boolean simplification might be less critical than writing efficient HDL that the synthesis tool can optimize?
Precisely. While a well-structured and logically minimized expression in HDL can still lead to better resource utilization and performance, the synthesis tools are quite sophisticated at optimizing the logic for the target FPGA architecture.
That makes sense. What about hazards in combinational circuits? How do you typically identify and deal with them, especially in asynchronous designs?
Hazards, those pesky temporary glitches. We can identify static hazards, where the output should remain at 0 or 1 but momentarily flips, by looking at the K-map for adjacent 1s or 0s that aren't covered by a single product term. For dynamic hazards, multiple transitions when only one is expected. It's more complex and often requires careful design and sometimes the insertion of redundant gates or using synchronous design methodologies.
Redundant gates, like adding consensus terms, right? Does that always guarantee hazard elimination? And are there any drawbacks?
Yes, adding consensus terms can eliminate static hazards. However, it increases the complexity and cost of the circuit in terms of the number of gates. It's a trade-off between reliability and resource usage. Synchronous design, where all state changes are synchronized by a clock signal, inherently helps in mitigating many hazard issues.
Synchronous design definitely simplifies things in that regard. Now moving on to common combinational modules like multiplexers. What are some interesting or less obvious applications of multiplexers beyond just selecting one of several inputs?
Multiplexers are surprisingly versatile. You can use them to implement Boolean functions directly from their truth tables, generate arbitrary waveforms, or even act as parallel to serial converters. Their ability to select data paths makes them fundamental in routing signals within larger digital systems.
Implementing Boolean functions with a mu-x. That's clever. You'd essentially connect the input variables, or their complements, to the select lines, and the desired output values, 0 or 1, to the data inputs, right?
Exactly. For an n-variable Boolean function, you can use a 2 n-to-1 multiplexer. It can be a very efficient way to implement complex functions, especially when the number of variables isn't too large.
What about decoders? Their primary function is usually seen as converting a binary code into a set of unique output lines. Are there any interesting ways they can be combined with other modules to achieve more complex functionalities?
Decoders are often paired with OR gates to implement Boolean functions in sum of minterms form. They're also crucial in memory addressing, selecting specific memory locations based on an address input. And combined with enable signals, they can be used to create more complex selection logic.
Ah, yes, using a decoder to generate the minterms and then ORing the relevant ones based on the truth table. That's a standard technique. What about encoders? Priority encoders, in particular, seem quite useful. Where do you see them frequently applied?
Priority encoders are essential in handling interrupt requests in microprocessors, where multiple devices might request service simultaneously. They identify the highest priority request and output its corresponding binary code. They're also used in keyboard scanning to determine which key was pressed first if multiple keys are pressed around the same time.
Interrupt handling is a classic example. It's interesting how these basic building blocks can be combined to create sophisticated systems. Have you seen any new trends or advancements in combinational logic design methodologies recently?
With the increasing complexity of integrated circuits, there's a growing emphasis on automated synthesis and verification tools. High-level synthesis, HLS, which allows designers to describe hardware functionality using higher-level languages like C++ or System C, is becoming more prevalent. This abstracts away some of the low-level gate manipulation.
HLS sounds like it could significantly improve design productivity. How does it handle optimization for area and performance compared to traditional HDL-based flows?
HLS tools employ sophisticated optimization algorithms to map the high-level description onto the target hardware. They explore different architectural choices, such as pipelining and loop unrolling, to achieve the desired performance and resource utilization. However, the quality of the generated hardware still depends on the designer's understanding of the underlying hardware and how to guide the HLS tool effectively.
That makes sense. It's still a tool that requires expertise to wield effectively. What about the impact of emerging technologies like quantum computing on classical combinational logic design? Do you see any potential overlaps or future implications?
That's a fascinating question. While quantum computing is fundamentally different, the principles of Boolean algebra and logic are still relevant in understanding and designing the control circuits for quantum computers. We might see hybrid systems where classical combinational logic interacts with quantum processors for specific tasks.
Hybrid systems. That's an interesting thought. So, the foundational knowledge of combinational logic will likely remain valuable even in a future with quantum computing?
Absolutely. The underlying principles of information processing and manipulation, which are at the heart of combinational logic, will continue to be essential, even if the physical implementation changes dramatically.
That's reassuring. Going back to more immediate concerns, what are some common pitfalls that junior engineers often encounter when designing combinational logic circuits?
Forgetting to consider all input combinations in the truth table, not properly handling don't care conditions, overlooking propagation delays and potential hazards, and not adequately testing their designs are common mistakes. Also, inefficient simplification of Boolean expressions can lead to unnecessarily complex and resource-intensive circuits.
Testing is definitely crucial. What are some effective strategies for testing combinational logic circuits, especially for complex designs?
Thorough testing involves applying all possible input combinations and verifying the outputs against the truth table. For complex circuits, simulation using HDL simulators is essential before physical implementation. We can also use techniques like fault simulation to assess the circuit's robustness to potential manufacturing defects.
Fault simulation. That's an interesting area. It sounds like you're injecting hypothetical faults into the circuit model to see if they can be detected by the test vectors.
Exactly. It helps us evaluate the fault coverage of our test set and identify any weaknesses. For critical applications, ensuring high fault coverage is paramount.
This has been a great overview of combinational logic design, B. You've touched on everything from the fundamentals to practical implementation and even future trends.
My pleasure, A. It's always good to revisit these foundational concepts and discuss how they evolve with new technologies.
One last quick question. When choosing between TTL and CMOS integrated circuits for implementing combinational logic, what are the key factors you consider these days?
Primarily power consumption and noise immunity. CMOS generally offers significantly lower power consumption, which is crucial for battery-powered devices and high-density designs. TTL traditionally had faster switching speeds but higher power dissipation. Modern CMOS technologies have narrowed the speed gap considerably and offer better noise margins.
So for most new designs, CMOS would be the preferred choice, unless there's a very specific requirement for ultra-high speed that outweighs power considerations?
That's a fair generalization. There might still be niche applications where specific TTL characteristics are advantageous. But for the vast majority of modern digital systems, CMOS is the dominant technology for implementing combinational logic.
Thanks for clarifying that, Bri. This has been incredibly insightful.
Anytime, A. Always happy to discuss digital logic.
Perhaps next time we can delve into the intricacies of sequential logic design?
Sounds like a plan. I'm looking forward to it.